lightning rod. So we have a cloud and it's a thunderstorm and lightning strikes everywhere. To protect our buildings, Franklin suggested to use a lightning rod. Lightning rod is a piece of conducting material, usually metal, that is placed on the top of the building that is connected with a wire to the ground. We already discussed that field lines are always perpendicular to the surface of the metal. So let's look how the surface of the metal goes. We have it's perpendicular over here, perpendicular over here, but at the end of the lightning we have something like that. So we would have field lines going straight up and then like on the picture. So we just try to preserve that it should be perpendicular to the surface of the rod. And the field lines are always largest near the sharp edges. It's true for every conducting material, and we're going to look at the next slide how we can model it in a simple way to show that exactly that the field lines are largest near the sharp tip of the rod and smaller near the flat side, and that create condition for the lightning to strike top of the rod and travel down the ground to protect buildings. Lightning rod model. Lightning rod can be modeled as two metal spheres connected by a metal wire. And so this is our sharp edge and this is our flat edge. Well, it's approximation, so why not? We're going to do it, I'm going to do it this way. It works. And what's important here in this setup to understand is that electric potential is identical on this sphere, and on this, because they connected with the wire. Remember I told you in the previous videos that inside a sphere, conducting sphere, like metal sphere, electric potential is always constant and it's equal value on its surface. Basically just how metal works. Electric field is zero inside the metal, but electric potential is a constant value inside the sphere. So as soon as we're connecting one metal sphere with another metal sphere by wire, we charges go from one to another until electric potential value will be the same on both spheres. And those values are electric potential in first sphere is KQ1R1, potential on a second sphere is KQ2 over R2. So we can continue and do the math. So KQ1 over R1, potential in the first sphere, that's this equation, is equal KQ2 R2. Doing cancel out case, we would get that the charges are related by this relationship. Q1 over R1 is equal to Q2 over R2. Doing a little bit more algebra, we can find also relationship between electric fields on a first small sphere and electric field on the second sphere. We can do it by using definition, how we calculate electric field is KQ1 over R1 squared. That will be E1, and E2 is equal KQ2 over R2 squared. And using relationship Q1 is over R1 is equal Q2 over R2. We can then write down that E1 over E2 is equal Q1 over R1 times R1. This is just that written differently, and for E2 we would have Q2 R2 times R2. This is just that, K cancels out. And so hence what do we have? Q1 over R1 is the same as Q2 over R2, hence they canceled out, and we're going to end up with R2 over R1. We found this expression. So the field, what does it tell us? That the field is largely near the surface of the smaller sphere, okay? So which one, if R1 is smaller, then electric field would be larger, okay? So sharp edges have large electric field. Large electric field causes nearby air molecules to be ionized. That creates a path for lightning to go and hit the tip of a lightning rod. And so this way we created a path for lightning to go down to Earth and dissipate. Now this is the next concept, discontinuous jumps. And this is kind of slide on the side. And it relates that potential energy and electric potential are continuous functions. They cannot have discontinuous jumps. Remember, I've showed you that electric field can be zero inside. It's a different color. It can be zero inside conductor metal, and then has huge jump and goes like that outside conductor. This situation is not possible for potential energy and electric potential. Just kind of hand-waving explanation why it's not possible, why potential energy and electric potential are continuous functions. Let's consider a particle that moves between 2 points A and B that are distance delta x apart. So potential energy then is equal F times delta x. If we divide this expression by delta x, I would get formula that force is equal negative potential energy, change in potential energy over distance. So if delta x very small, then the change in potential energy must be also very small. Otherwise, F would be very large, so it is impossible. So this understanding that force cannot be extremely large between 2-point charges gives us conclusion that electric potential and electric potential energy are continuous functions. Next idea, shielding the electric field. So lightning rods are important, they're helpful. However, what also important to remember is that inside conducting sphere, electric field is always zero. This is a wonderful fact. But it also means that even inside the metal there is a cavity. Electric field in this cavity is also going to be zero. And that is behind electric shielding. So if you want to create a place where you're safe from electricity, you go inside the metal box and be in metal cavity. There is electric field is always zero over there. For example, if in case of lightning storm, your car is the best place to be because electric field inside the car is going to be zero, and it will shield you from the lightning strike wonderfully. Let's solve problem 16. Find the electric potential V at the center of electric dipole in a figure 18.6. So we already seen this figure before in problem 6. How we would solve this problem? Electric potential V from a point charge at the distance is given by KQ divided by R. So in the middle we would have V is equal K negative Q over L plus K positive Q over L. The first part created by this charge and the second part created by this charge. Obviously they cancel out and the answer is 0. So potential in the middle of electric dipole is 0. By the way, electric dipole is just negative charge, positive charge at the given distance, and they always stay like that. And also, if you remember what we did in the problem 6, we found that potential energy in the middle is 0. So then using definition that potential is equal potential energy over charge, you can also get 0. Problem 22. How much work is required to push an electron through a region where the potential change is 45 volts? Assume electron moves from a region of low potential to a region of high potential. So, given electron, negative 1.6, 10 to negative 19 coulombs. Change in potential is 45 volts. Find work. Work is equal change in potential energy. Hence, equal electrons times delta V. Hence, negative 1.6, 10 to the negative 19 times 45 volts. Coulombs, volts. Hence, we're going to get negative 7.2 times 10 to the negative 18 joules. That is your answer. So what does that actually mean? Well, it means that electron really want to go to the area of higher potential, and we have to slow it down for it not to really speed up there, and work that we do is negative, like friction force doing negative work. We're slowing down electron. Let's solve last problem, 33. Given ring of charge, radius r, charge per unit length lambda, find electric potential at the center of the ring, over here. The easiest way to solve this problem is to break it on little parts, little charges delta Q all around the ring. Then find electric potential at the center due to single charge and add them all up. Delta Q is equal charge per unit length times delta L. Delta L is little tiny delta L over here for every charge all around the ring. Potential due to delta Q is equal K delta Q over R, distance from this charge to the center of a ring. Plug in delta Q, K, delta L, lambda over R, and this is actually delta V, potential created by little delta Q. To find total potential in the center, we need to add up all these contributions, delta V. We can write it this way: sum K lambda over R, delta L. This is all constant. They can go right here. So we would have K lambda R sum delta L. And what is sum delta L? This is just, we have to sum all around the ring. It's going to give us circumference. So it is K lambda R 2 pi R. R cancel out. So our final answer is K 2 pi lambda. That's pretty much it.